Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really intriguing question. Can large language models, or LMEs, truly reason outside the box when it comes to mathematics? We're basing our conversation on a recent piece titled Omega, Can LLMs Reason Outside the Box in Math?
Yeah, I saw that. It's a pretty loaded question, right? I mean, we've seen LLMs do some impressive things with math, but is it actual reasoning or just sophisticated pattern recognition?
Exactly. That's the core issue. I'm inherently skeptical of the idea that these purely statistical models can truly reason in a way that resembles human mathematicians. It feels like we're giving them too much credit based on impressive, but ultimately superficial, results.
I'm not sure I agree entirely. I think there's a possibility they are doing something beyond pure pattern recognition, even if we don't fully understand what it is yet. Maybe they're implicitly discovering new mathematical structures or relationships that we haven't explicitly taught them.
That's an interesting point. It kind of ties into some of my own thinking lately about how we can draw inspiration from neuroscience to build more intelligent machines. The fact that LLMs can perform certain mathematical tasks at all suggests that there might be some underlying algorithmic principles at play that we could potentially leverage. It reminds me a bit of how the brain builds internal models of the world. The Othello world model research got me thinking, could these models be constructing internal mathematical worlds that allow them to explore different possibilities?
That's a fascinating analogy. I've been thinking about the sheer scale of data these models are trained on. It's almost like they're absorbing the entire landscape of existing mathematical knowledge. And with that much data, maybe they're able to identify patterns and relationships that would be impossible for a human to see. I mean, could it be that more data is simply the key? Are we on the path to AGI through sheer computational power and massive data sets?
I seriously doubt it. More data might refine the algorithms, but it doesn't change the fundamental limitations of the underlying architecture. They're still fundamentally statistical machines, and I don't believe that statistical pattern matching alone is sufficient for true mathematical reasoning. We need something more symbolic, something that can understand and manipulate mathematical concepts in a way that transcends simply recognizing patterns. Think about Gödel's incompleteness theorems, for example. How could a statistical model ever grasp the implications of something like that?
I think the interesting question then becomes, what is that something more? I suspect it has to do with the way the model represents and manipulates abstract concepts, perhaps by implicitly translating between different coordinate representations. Imagine trying to solve a complex geometry problem. Sometimes, switching from Cartesian to polar coordinates makes the solution much easier. Could LLMs be doing something similar internally, without us even realizing it? It's not just about math, it is also about spatiotemporal reasoning.
Okay, but let's break this down. When you say reasoning outside the box, what exactly do you mean? Are we talking about proving new theorems, discovering entirely new branches of mathematics, or just solving problems that haven't been explicitly seen in the training data?
I think it's about that ability to generalize, right? To take what you've learned in one context and apply it to a completely new and unexpected situation. It's about demonstrating a deep understanding of the underlying principles rather than just regurgitating memorized solutions. For example, can an LLM solve a novel geometry problem that requires integrating multiple concepts it was never explicitly taught to combine? Can it come up with a new proof or theorem?
Right, it's about understanding the why, not just the how. An LLM might be able to correctly solve a differential equation, but does it understand the underlying concepts of rates of change and accumulation? Does it understand the relationship between the equation and the physical system it's modeling? I'd argue that without that deeper understanding, it's not truly reasoning.
And to be fair, even many human students struggle with the why behind mathematics. They can learn the algorithms and solve the problems, but they don't necessarily grasp the underlying concepts. So are we holding LLMs to a higher standard than we hold ourselves?
Well, I think we should be holding them to a higher standard if our goal is to create true AGI. If we want machines that can truly reason and solve problems in a general purpose way, then they need to have a deeper understanding than just pattern recognition. And I think the key to that deeper understanding is the ability to represent and manipulate abstract concepts in a flexible and adaptable way. Spatiotemporal reasoning is one key element of how we reason.
It almost feels like we're talking about different levels of intelligence here. There's the surface level intelligence of being able to perform specific tasks, and then there's the deeper level intelligence of being able to understand the underlying principles and generalize to new situations. Current LLMs seem to excel at the surface level, but they're still lacking in that deeper understanding. It's like some of the observations around language. An LM can mimic aligned behavior without necessarily understanding alignment. That raises ethical questions, right? What constitutes true intelligence then?
Exactly. And that's why I'm so interested in neuro-symbolic approaches. Combining the statistical power of neural networks with the symbolic reasoning capabilities of traditional AI seems like a much more promising path to achieving true intelligence. Imagine a system that can not only recognize patterns in data, but also formulate and test hypotheses, derive logical conclusions, and build formal mathematical proofs. That's the kind of system that could truly reason outside the box in mathematics.
Okay, I see where you're coming from. But isn't it possible that these two approaches, deep learning and neuro-symbolic AI, are actually complementary? Maybe we can use deep learning to learn the low-level patterns in data, and then use neuro-symbolic AI to build higher-level representations and reasoning mechanisms on top of those patterns. It's like using deep learning as a kind of sensory input for a more traditional AI system.
Yes, and that's where thinking about spatial reasoning and different coordinate systems comes in. The deep learning part could be about taking the data from the environment, the sensory input, as was said, and translating it into a spatial representation. Then the neuro-symbolic AI could take over from there to reason. So it's really about translation between representations.
That resonates with me. Think about how the brain works. We have sensory input that's processed by neural networks, but then that information is integrated and processed by higher level cognitive systems that use more symbolic representations. So maybe we can build AI systems that mimic that hierarchical structure.
I agree. It's about finding the right balance between the two approaches. We need the pattern recognition capabilities of deep learning, but we also need the structured reasoning capabilities of symbolic AI. And we need to find a way to seamlessly integrate the two.
So let's bring it back to the original question. Can LLMs reason outside the box in math? Based on what we've discussed, it sounds like the answer is maybe, but not really. They can perform impressive feats of pattern recognition, but they lack the deeper understanding and reasoning capabilities that would allow them to truly generalize to novel situations.
I'd say it's more like they're potentially reasoning outside the box, but we don't have the tools to properly understand or evaluate what they're doing internally. We need to dig deeper into their internal representations and see if they're implicitly discovering new mathematical structures or relationships. Maybe they are doing coordinate translations.
And that brings us to the crucial question of how we do evaluate their reasoning abilities. Current benchmarks are often based on performance on specific tasks, but that doesn't necessarily tell us anything about their underlying understanding. We need to develop new evaluation metrics that can assess their ability to generalize, to transfer knowledge, and to reason in a truly creative and innovative way, perhaps inspired by neuroscientific methods.
Yes, and that's where neuro-symbolic approaches have a potential advantage. Because they're based on symbolic representations, we can actually inspect their internal reasoning processes. We can see how they're manipulating symbols, deriving conclusions, and building proofs. That gives us a much clearer understanding of their reasoning abilities than we get with a black box deep learning model.
But isn't it possible that we're just imposing our own human biases on the evaluation process? Maybe LLMs are reasoning in a way that's fundamentally different from how humans reason, and we're just not able to recognize it because we're looking for something that resembles our own thought processes.
That's a fair point. We need to be careful not to anthropomorphize these systems. But I still think it's important to try to understand their internal representations, even if they're different from our own. The internal representation may be about translating coordinate systems. We just need to figure it out.
It's a tricky balance, right? We want to understand these systems on their own terms, but we also want to ensure that they're aligned with our values and goals. And that raises a whole host of ethical questions about what it means to build truly intelligent machines.
Absolutely. We need to be thinking about the ethical implications of AI from the very beginning, not as an afterthought. And that includes thinking about how we can ensure that these systems are used for good, not for harm.
Okay, so where do we go from here? What are some promising avenues for future research in this area?
From my perspective, I think it's crucial to explore how we can integrate neuroscientific findings into AI design. How can we use our understanding of the brain's architecture and algorithms to build more intelligent and adaptable machines? I'm particularly interested in how we can model the brain's hierarchical structure and its ability to build internal models of the world. The work on fake alignment has made me realize we need to understand the neurobiological underpinnings to truly evaluate and ultimately guide these systems. If we can pinpoint the neural correlates of human-like alignment in the brain, perhaps we can introduce those mechanisms into AI models.
I think we need to continue pushing the boundaries of deep learning, exploring new architectures, training techniques, and datasets. We need to see just how far we can go with this approach. If more data is the key, how can we ensure that the data we feed to these models is representative and avoids potential biases? What are the limitations of relying on existing datasets, and how can we effectively build and curate datasets from scratch to facilitate the next leap in model capability? Also, diving deeper into how LLMs perform on complex mathematical tasks could offer more profound insights into their capabilities.
I think we need to seriously invest in neuro-symbolic AI, exploring new ways to combine the strengths of neural networks and symbolic reasoning. We need to develop models that can not only recognize patterns, but also formulate and test hypotheses, derive logical conclusions, and build formal proofs. For example, how can LLMs represent mathematical structures internally? Are they merely manipulating symbols based on observed patterns, or do they utilize a more structured symbolic representation that resembles how humans process these ideas? If LLMs are struggling to reason outside the box in mathematics, it highlights the significant limitations of current deep learning paradigms and points towards the need for fundamentally different architectures and approaches. Purely statistical models will never be able to achieve true intelligence in fields that require symbolic reasoning.
I think we need to focus on developing algorithms that can represent and manipulate abstract concepts in a flexible and adaptable way. That probably involves spatiotemporal reasoning, and it definitely involves the ability to translate between different coordinate representations. We need to move away from brute force approaches and start thinking about the fundamental principles that underlie intelligence. I'm interested in how we can develop a core algorithm for AGI that can seamlessly translate between different coordinate systems. What are the theoretical limits to how many and what types of systems are required? Is there a way to build this ability into a system rather than it being learned through brute force searching in data?
Those are all great points, and it's clear that there's still a lot of work to be done in this area. But I think it's also incredibly exciting to see the progress that's being made, and I'm optimistic about the future of AI. It will require effort to translate neural structures to language model architectures.
Yeah, it's definitely a field that's full of surprises. Who knows what we'll discover next?
Hopefully, we'll discover something that actually resembles true intelligence.
And that can seamlessly translate between coordinate systems.
Well, that brings us to the end of our discussion for today. Thanks everyone for joining us on Cognitive Spirals. We hope you found this conversation thought-provoking, and we look forward to exploring more fascinating topics in the future. Join us next time.